Okay, so if we notice that the distance between a point on the graph of y equals 1 over x and the y-axis approaches 0 is the point moves vertically along the graph and away from the origin. In other words, if I'm moving away from the origin and going upwards, origin being 0, 0. If I'm moving vertically along the graph and away from the origin, away from 0, 0, you're going to notice that my graph gets closer and closer to y, the y-axis, or x equals 0. Looking at it the same direction on the negative side, the further and further we get away from 0, moving vertically, the further and further down we go. That creates asymptotes, which is a line that our graph is never going to cross. So we'll have a vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0. If I move along the x-axis the same way I did the y-axis, moving along the x, you're going to see that it gets closer and closer to 0. So as x gets greater and greater, it gets closer to 0. And we saw in the last section that the limit as x approaches infinity of 1 over x was 0. Because x keeps getting bigger and bigger, and it's 1 divided by that, which makes this keep getting smaller and smaller and closer to 0. So that's how we have the horizontal asymptote. Now, if I was looking at x, the limit as x approaches 0 of this graph, I'd be looking at what is y getting closer and closer to. And it doesn't get closer and closer to anything. The y just continues going up. So the limit as x approaches 0 from the right-hand side would be infinity. So we can learn from this that if we have a vertical asymptote, then whatever that vertical asymptote is, the line x equals a is a vertical asymptote of the graph of a function. If either the limit as x approaches a from the right of the function is positive or negative infinity, or if it approaches from the left, we have positive or negative infinity. So as soon as I find my limit and I find that it's either positive or negative infinity, as x approaches some number, either from the right or left, I know that that's where there's an asymptote, a vertical asymptote, that is. So now if I have a question that's asking me to find the vertical and horizontal asymptotes of the curve, then what I need to do is I need to figure out where those asymptotes would be. And so the first thing I'm going to look for is what would give me an undefined from the denominator. And that would be if I had a 0 in the denominator, right? And so if I had a 0 in the denominator, I'm going to figure out what that would be. X plus 2 equals 0. That would give me x equals negative 2. So I'm interested in finding two different limits here. I'm looking for the behavior as x approaches either positive or negative infinity. And then I'm looking for the behavior as x approaches negative 2. And by finding those two things, I'll be able to know where the asymptotes are. So the easiest way to do this would be to go back to Algebra 2 and rewrite our rational function as a polynomial function. It's a rational function because it's a function divided by a function, and rewrite it using long division. X plus 3 divided by x plus 2. So now whenever I actually solve this out, how many times does x go into x? Once. And then flip your sign. X times 1 is 1x. And you're subtracting it, that's why you flip your sign. And then 1 times 2 is 2. You're subtracting that as well. X minus x is 0. 3 minus 2 is 1. Then how many times does x go into 1? It doesn't at all. So that's our remainder. So it's 1 plus 1 over x plus 2. So we can just rewrite y as 1 plus 1 over x plus 2. Whenever we look at this equation now, I can see what's happening. I have a graph of 1 over x here, the 1 over x plus 2 anyways. The 1 that's out in front gives me my horizontal asymptote. Then this one here gives me my vertical asymptote, whatever my remainder is. Because now I can look at this first one, and that gives me the line 1 for my horizontal asymptote. It was going so well, and then it just like fell off on me. And then this line, 1 over x plus 2, is the vertical asymptote. Now think about your shifts of function. If it's 1 over x plus 2, then that means that it's going to be the original equation, 1 over x, shifted to the left 2. And that's my vertical asymptote. So there's 1 and there's 2. I'm at the line -2. And now I'm just taking the function of 1 over x and drawing it out. And you really don't even have to do this part of it. Once you see that I have 1 is my answer, that's my horizontal asymptote. So the question asks you to find the vertical and horizontal. The horizontal is at y equals 1. And the vertical is then at x equals -2, just based on the transformation. Questions? We can also have curves with infinitely many asymptotes. If I look at the function y equals the secant of x, which is, if you remember from our trig, y equals 1 over the cosine of x. It gives us this function here with these hoops. It's like parabolas. But it's not exactly a parabola. because I can't have asymptotes here and here and here, 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 and here. So it's a lot of different asymptotes to try and track. And we don't even have all of them on our screen. If I continued all the way to the right or all the way to the left, it would just keep going forever. So it's important to realize that the vertical asymptotes both have multiples of pi over 2. Because we really didn't get a pre-calc class because of the pandemic, you're probably not going to have to worry about your trig functions for this section nearly as much. Just wanted to highlight the fact that you could have an endless amount of vertical asymptotes. That's about it. The way that you would figure out where each one of them was is we would take our first asymptote, which is here at pi over 2, and then we would just call this plus pi times x. Because it's going to keep repeating itself at an interval of pi. So if I add pi to pi over 2, it gives me 3 pi over 2. That's my next asymptote. If I add pi again to 3 pi over 2, it gives me 5 pi over 2. That's my next asymptote. Same thing here, looking at the negative. Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. Your tangent function is very similar, though it doesn't look the same hardly at all. You're still looking at the same basic graph, or the same basic concept at least. So if I'm looking at tangent, let's see how horrible I can draw this. My tangent function starts down here, going on forever, because it does have an asymptote. And it comes up to pi over 2. Yep, that was terrible. Why don't I use Desmos? So using Desmos, I can look at this much easier. And you can see that I have a line at pi over 2. That's an asymptote. And then my next one, just like before, I have the same thing at negative pi over 2. And then if I add pi to each one, you're going to see that it just keeps creating more and more asymptotes. And this goes on forever. So we wouldn't want to have to list them all out and say pi over 2, 3 pi over 2, 5 pi over 2. So just by saying pi over 2 plus pi x, that tells us that it's going to be going on forever. Meaning I can add whatever x in I want, and it's going to create an asymptote. I don't think that would work on Desmos, but it's just something to be aware of. If you have infinitely many, find out what interval it's going to. So we found that there's a gap of pi in between these two, and then just make it pi times x. Add it onto your first one, or any one really. Okay, here we have another graph we're going to try to find the asymptotes of. And so if I go back to my same formula, same basic formula I had, which was setting up a polynomial division of x squared minus 3 over 2x minus 4. So I need to figure out how many times 2x goes into x squared. In order to do that, I would have to multiply this by an x to get x squared. But then 2 goes into 1 1/2 times. So it would be 1/2 x. Now I multiply 1/2 by 2 and subtract it. That should give me 1/2 x by 2x and subtract it. That should give me x squared. If it doesn't, you did something wrong. Half of 2 is 1. X times x is x squared. Then do half x times negative 4. That's going to give me 2x. Flip your sign because we're subtracting. It's going to turn into a plus 2x. Now I will say that I have committed a cardinal sin here by not filling in a gap. I should have made a plus 0x and then plus 3, because you have to remember to fill that gap in. You can never leave. It's a minus 3. What's happening? Okay, so 0x plus 2x, that gives me 2x. And then bring down your minus 3. So then, how many times does 2x go into 2x? It goes in once. 2x times 1 gives me 2x. And I'm subtracting that. Then 1 times negative 4 is negative 4. I'm subtracting that as well. That gives me plus 4. Those cancel. And I just have 1 left as my remainder. So this would be plus 1 over 2x minus 4. Now, if you remember the last time we did this, we just had a number in front, not a 1/2 x plus 1. And that was because we were trying to find a vertical or a horizontal asymptote. Like in that last example here, whenever we ended up with just a number, it created a horizontal asymptote. This is not just a number, it's an equation, which means we don't have a horizontal asymptote in this case. We have what's called an oblique asymptote, which means that whenever I try to graph this, I'm not going to have any horizontal asymptote. But if I look at what this part of it gives me, 1/2 x plus 1, you have to go back to Algebra 1 now and remember how to graph that. So to graph that, you start with your y-intercept, go up 1, make a point. Then I go up 1 and over 2. And that creates this line, which is where my asymptote is going to be. So I'm not going to have a horizontal, I'm going to have a vertical asymptote. Or not a vertical, an oblique. Now I have to find my vertical asymptote. So in order to do that, find my vertical asymptote, I need to look at what is happening to this part of the equation. So if my original function would have been a 1 over x, then what happens here is this is 2x minus 4. I can factor 2 out. It gives me 1 over 2 times x minus 2. x minus 2 indicates that my function is being moved to the right by 2 units. And so that's where my vertical asymptote comes in at. And so now I can take my graph and graph it kind of like this. So just by finding my asymptotes, I can figure out what my graph looks like, and it's going to be like that. Okay, so that's really the end of the new material. Tomorrow in class, we are going to do a lot of examples as opposed to learning new stuff. We'll just do examples tomorrow and go from there.